Students, welcome to another video of calculus. Today we will discuss the D'Alembert's ratio test. So today's topic is D'Alembert's ratio test. To find the convergence of given sequence, we can use this D'Alembert's ratio test for the convergence of sequence. Now the statement of that test is, let x is equals to xn, this is notation of sequence, be a sequence of real numbers, be a sequence of positive real numbers with a sequence of positive real numbers such that limit n tends to infinity, x n plus 1 upon x n. This is n plus 1 and n are the suffix to x, that is x n plus 1 upon x n is equals to L, that is the limit of if we have given the sequence x n, and from that we can find the x n plus 1. If we take the ratio of x n plus 1 upon x n and take limit n tends to infinity, then this limit exists, that is, and limit exists and is equals to L, this limit L which is exist. Now if that limit L is less than 1, if L is less than 1, then our sequence which is x is equals to x n, the sequence x n is convergent, the sequence converges and limit n tends to infinity, x n is equals to 0. This is the D'Alembert's ratio test for the convergence of sequence, D'Alembert's ratio test. We have given x n be in a sequence of positive real numbers. If the ratio, that is, if this limit of x n plus 1 upon x n is equals to L, this limit exists, then if this limit is less than 1, then we can say that given sequence x n is convergent, and also limit n tends to infinity, x n is equals to 0. So using this test we can solve the example. So we will take the example on this. Suppose the example is show that the sequence x n converges, sequence x n is equal to, suppose, n upon 2 raised to n converges to 0. Show that the sequence x n is equals to n upon 2 raised to n converges to 0. So here clearly we have given that x n is equals to this n upon 2 raised to n. We have given that x n is equals to n upon 2 raised to n. If the given sequence is in the form of n upon some number or n plus 1 upon n, or that is, if the given sequence is in the form of n, then we can use this ratio test. Here x n is equals to this n upon 2 raised to n. From that we can find x n plus 1. So we have to replace n by n plus 1 in this equation, then we can get this n plus 1 upon 2 raised to n plus 1. Just substituting n plus 1 instead of n, we get this x n plus 1. Now we have to find, by using this, to use this test we have to find the limit of x n plus 1 upon x n. If that limit is less than 1, then we can say that sequence convergent. Now here, first of all we will take the ratio, that is limit n tends to infinity, x n plus 1 upon x n is equals to. So here x n plus 1 is n plus 1 upon limit n tends to infinity as it is, x n plus 1 is equal to this n plus 1 upon 2 raised to n plus 1 divided by x n. So we can write it as, so x n is n upon 2 raised to n. So dividing by this n upon 2 raised to n, we can simplify that 2 raised to n upon n. This is multiplication sign. Now clearly you can see that this limit n tends to infinity 2 raised to n plus 1, we can write 2 raised to n plus 1 as 2 raised to n into 2. So 2 raised to n, 2 raised to n gets cancelled. So n plus 1 upon n into 1 by 2. Since we can write this 2 raised to n plus 1 as 2 raised to n into 2. So 1 by 2 n plus 1. We can again simplify this 1 by 2 outside the limit n tends to infinity. If you take n common and divide n on both sides, so just separating the divisor or separating denominator, n by n is 1 plus 1 by n. Now limit n tends to infinity, n plus 1 by n. If n is equals to infinity, then 1 plus 1 upon infinity, 1 upon infinity is 0, 1 plus 0 is 1 plus 0 is 1, 1 into 1 by 2 is 1 by 2. So this limit is 1 by 2, which is less than 1. So this will therefore by ratio test we can write sequence xn, which is equals to n upon 2 raised to n is convergent, and limit n tends to infinity xn is equals to 0. This is the statement of this D'Alembert's ratio test. Here limit n tends to infinity xn plus 1 upon xn is equals to L, and that limit L is less than 1, then given sequence xn is convergent, and this limit n tends to infinity xn is equals to 0, that is limit n tends to infinity given xn was n upon 2 raised to n is equals to 0. Hence the sequence is converges to 0. Hence the solution of given example by D'Alembert's test. Now we will see some other examples directly substituting the limit. So first example is establish or check whether the following sequences are convergent. Check the convergence of the following sequences. Check the convergence of the following sequences. First sequence is xn is equals to n upon n plus 1, n upon n plus 1. We have to just find the limit n tends to infinity xn. So here limit n tends to infinity xn is n upon n plus 1. If you take the n common from the denominator, we get n upon n. So here n plus 1 by n. Now n gets cancelled. So the remaining term is limit n tends to infinity 1 upon 1 plus 1 by n. Now if you substitute n is equals to infinity, that is limit n tends to infinity 1 upon 1 plus 1 upon infinity is 0, 1 upon 1 plus 0 is 1. So 1 upon 1 is 1. So limit of given sequence is 1. Therefore the given sequence xn converges to 1. Now the second sequence xn is given as xn is equals to, suppose, 2n square plus 3 divided by n square plus 1. 2n square plus 3 divided by n square plus 1. Now to find the limit of given sequence, limit n tends to infinity xn is equals to limit n tends to infinity this 2n square plus 3 divided by n square plus 1. Now we can just rearrange this as, which is equals to this limit n tends to infinity 2 times n square plus 1 plus 1. 2 times n square plus 1 means 2n square plus 2 plus 1, that is 2n square plus 2 plus 1 is plus 3. So 2n square plus 3, we can arrange 2n square plus 3 as 2 times n square plus 1 upon 2 times n square plus 1 plus 1 divided by this n square plus 1 as it is. Now here if we divide by n square, then we get limit n tends to infinity 2 n square plus 1 n square plus gets cancelled plus 1 upon n square plus 1. Now this, if we put limit n tends to infinity, 1 upon infinity is 0. So, sequence of limit of given sequence is 2, that is the given sequence xn converges to 2. Now, the next example is give an example of give an example of two divergent sequences x and y such that their addition is convergent, such that first their sum x plus y converges, and b is their product x into y is also converges. We have to give an example of two sequences which are divergent, and we have to prove their addition and their multiplication is also convergent. Divergent means their limit does not exist. Now, if we take x is equals to xn, the sequence xn is equal, suppose 0, 1, 0, 1, 0, 1 and so on, this sequence xn, then clearly this sequence is divergent because there are two subsequences of this sequence. There is no need to prove that such sequence. You can clearly say that 0, 1, 0, 1, 0, 1 is not converges to a particular limit. Sequence converges to particular limit L whenever all the terms of that sequence for any n greater or equal n, all the terms of maximum terms are very close to that limit L. So, here clearly 0, 1, 0, 1. If we use the epsilon delta definition and take epsilon is equal suppose 1 by 2, and then for any L, for any limit, and if we draw the epsilon neighborhood of that point, suppose L is, if we take L is limit and draw the epsilon neighborhood suppose 1 by 2, then there is not more terms of this. So, clearly this sequence is divergent. Xn is equal to this, and suppose y is equals to yn is equals to, first term is 1, then 0, then again 1, 0, 1, 0 and so on. Clearly these both the sequences are divergent. X and y are divergent sequences because their limit does not exist. On contrary, we suppose the limit of this sequence exists, then all the terms, maximum terms of this sequence are must be very close to that limit. Then for all epsilon positive, that limit must be satisfied. If we take epsilon is equal suppose 1 by 4, then there are few terms, that is half of these terms are close to that limit L, but not the remaining. So, for a particular n, we cannot find the capital N such that epsilon delta definition is satisfied. So, xn and yn both the sequences are divergent sequences, but if we take their addition x plus y, that is the addition. So, 0 plus 1 is 1, again 1 plus 0 is 1, then 0 plus 1 is 1. So, this sequence is constant sequence, and clearly this sequence is converges to limit 1. This x plus 1 is constant sequence of 1, and hence it is convergent. Also, x into y, that is the product of two sequences. So, 0 into 1 is 0, again 1 into 0 is 0. So, similarly 0 into 1 is 0, again this sequence is constant sequence of 0, again this x into y is constant sequence of 0, and hence again it is also convergent. So, xn is equals to this and yn is equals to this are the examples of divergent sequences such that their addition as well as multiplication is convergent. Hence, the solution of this example.